In this video, we're going to look at generating variables which are drawn from an exponential distribution. And again, we're going to use the inverse Cdf method, the inverse cumulative distribution function method. And again, we're going to generate single random samples which are uniformly distributed, and then appropriately convert them using the inverse Cdf function into the distribution of our choice. So we're going to look at the exponential distribution because, of course, there are many physical systems for which producing samples which have this PDF are very important. A good example of this is looking at the absorption of particles in matter, for example, photons traveling through an absorbing medium. If they have a mean free path of a given value, say 10 centimeters or so, then every mean free path, approximately 1 over e of those particles are left over. So the distribution of intensity as a function of depth, this PDF should be an exponential. So using the inverse CDF, this cumulative distribution function is given here. If we scroll down, we can see what form it has. So the PDF goes as e to the minus x over lambda. So this is slightly misleading if you're thinking of lambda as being the mean free path. It should be x over lambda. So therefore the cumulative distribution function is 1 minus e to the minus x over lambda. So therefore the inverse CDF, which is very similar to this quantile function here, if we scroll down the bottom we can see how to generate samples. We can go down to here, let's have a look. Generating exponential variates. So you can see that it's an explicit formula given on this Wikipedia page. We wish to sample uniform variates u drawn on the unit interval 0 to 1, and then we calculate the inverse of that CDF, the cumulative distribution function. And in the case of the exponential distribution, this has a nice closed form, which is log of 1 minus u. So to draw samples t, which are drawn from this exponential distribution, we generate many samples u and convert them to samples t by doing this scaling. Remembering, of course, that in this page here, this lambda here does not represent the mean free path. It's actually 1 over that value. So let's look at how we do that on the left-hand side. Here's the exponential sample in Matlab. So as usual, I'm generating a number of samples, in this case 1000. So to begin with, I have a for loop where I generate a large number of samples, 1000 samples, and for each sample I draw a uniform random variate, that's u, and I use this formula here. I'd use minus log of 1 minus u to generate a single exponentially distributed variate, and you can see there's no lambda in here yet, so this should have this should be representing a unit mean free path. So I'll run it and I'll get a histogram. And there it is. So that is an exponentially distributed set of samples. Now, say if I want to represent a situation where I have a mean free path, which is some value, let's put that in. So I'll say lambda here equals, say, 5, and this can be any unit I like, so I could make it 5 centimeters if I like, or 5 meters, it doesn't really matter. So in order to scale those samples, I simply have to multiply them by lambda. So I run it again, and you can see that now the scale on the horizontal axis has been increased, and now 1 over e of those samples make it to values bigger than 5. Right? And you can draw on that distribution for yourself if you wish. Now you can see here that on line 12, that I'm drawing numbers, I'm doing a calculation based on uniform variates drawn on the interval 0 to 1. So the explicit formula for this CDF is this. However, look closely at this 1 minus u. So for each uniform variate between 0 and 1, I'm simply taking 1 minus that number. But 1 minus u, where u is a random number from 0 to 1, is the same thing as u. So I can just replace that 1 minus u with u, as so, and that will give me exactly the same distribution. But what it's done is it's saved me a small calculation. I don't have to do 1 minus each one of those 1000 random numbers, so it should run a little bit faster. So I can run that again, and you'll see it's absolutely identical, as we would expect. Okay, run it again. There it is. Now, that's almost the complete formula for doing it rather quickly. And of course, I don't need to define this intermediate sample u. I can simply take the rand function here. I can type log of rand here. And now I have a nice single line definition of which gives me an exponentially distributed random number. So I'm going there. And hey presto. Now, what you can do then, of course, is if you want to figure out what that lambda value is, and imagine I have a set of random samples, and I wish to obtain the value of lambda, what I need to do is I need to fit an appropriate exponential function to this. Of course, I take the log of the density of these numbers, how many samples are in each of these bins. So I can do that, but if I do help hist, I can find out the other way to use the hist function, which is to extract out the number in each bin and the position of the bin. So I write instead here, I write n comma x equals hist of those values, and I select explicitly here 20 bins. Then of course I can plot underneath, I can plot the x values and the number in each of those bins. So let's try that. I'm going to run that. And there we are. Perhaps I should plot it as some red circles just to show explicitly that these represent the same things we had before. So these are the same height as the histogram bins that we just had in our histogram. And of course what I can do now is I can take the log of those n values. So if I take the log of all those n values, remembering of course that n is an array, just like x is an array, and I take the log of all the numbers in that array, I run that again, and I should get, here we go, I should get a straight line. So the gradient of that line is just 1 over lambda, where lambda is the mean free path. And you will see that occasionally there are samples down here with very, very low values. You can see actually these ones here are probably not correct. I'll leave you to have a think about what happens when I have 0 samples in a particular bin. You can see something going on here. So you need to pay attention to that when you want to fit the gradient of this line. You might have to take those samples out. That's a little nicety which makes for an interesting afternoon. So that's how we generate exponentially distributed random numbers.